So in this first video for Chapter 14 test review, I want to go over some of the basic chemical reactions that you see with acids and bases. Now, the first two sometimes is referred to as hydrolysis reactions, where the acid or base reacts with water and then you produce something new. Just a quick little tour, okay? So this is actually already showing you the full reaction. Okay, if you see hydroxide being produced on the product side, then you're dealing with a basic solution or a base. If you see hydronium being produced, then you're dealing with an acid. And you should know the names of these two ions. Very important in acid-base chemistry. Now, in this particular problem, what we're wanting to do is really focus in on the Bronsted-Lowry model. And that's by far the most common one that you deal with. I know Arrhenius was mentioned. You should know the basics of Arrhenius, where if it's an acid, it produces a proton or hydronium, and if it's a base, and it produces hydroxide in solution. On one level, you could probably apply Arrhenius model here, but the main feature that you see here is a proton transfer, right? That's characteristic of a Bronsted-Lowry acid-base model. So my little symbol for the proton is just H+, and that is literally just a proton, right? It's just one of those subatomic particles we learned at the beginning of the semester. Sometimes these are fairly loosely attached, so when they are, when those types of molecules are brought with something that can accept them, then you get this proton transfer that we refer to as the Bronsted-Lowry model for acid-base chemistry. And now, since the full reaction is already given to you, notice what's happening. What's happening to the water? Water had two protons to begin with. It only has one at the end. Therefore, you get this proton transfer going in that direction. Here, it's just the opposite. It had two protons originally. Now it has three, and so you had a transfer in that direction. Right, so the molecule that donates the proton, that's our acid. And then whichever one accepts the proton, that's their base. I could do the same thing here, right? Donate, that's acid. This is our base. Notice that water, if water's paired up with a base, it acts as an acid. If water is paired up with an acid, it acts as a base. So water's one of the molecules that can play both roles in a reaction depending on what it's paired up with. Let's focus in on this basic reaction just for a little bit. And notice that nitrogen there. One of the common bases you find in particularly organic chemistry are these nitrogen-containing compounds. We're not going to get into the details, okay? But if you see a nitrogen in a molecular formula like this, anticipate that it may act as a base, and that's what's happening here. And you can see that. Again, the nitrogen here is all by itself. Now it's paired up with that hydrogen. Right, so it has accepted a proton from the acid. Now to finish off the problem, there's these labels that we use. What happens to the base? The base gains a proton. Well, what we call this now is conjugate acid. And then the acid, when it donates a proton, when it loses that proton, now we call this a conjugate base. So again, to go from the acid to the conjugate base, remove proton. To go from the base to the conjugate acid, we gain or add proton. And we see the same thing down here. What's happening to the water? Acts as the base. Now we have this as a conjugate acid. And then the acid loses a proton, and we refer to it as a conjugate base. Before I move on from here, I just want to point one thing out. When you see this single-headed arrow here, what that's referring to is a strong acid. Now, you see the single-headed arrow used in other places. Okay, I'm focusing on just the acids here. You can talk about it with the bases as well, but again, this is a strong acid. That means that nitric acid, which is a common acid, completely dissociates in solution. Okay, so at the end of this, once you've added the HNO3 to the water, practically no HNO3 is remaining. All the protons have been transferred, and you're just left with these molecules, these ions in solution. For this class, we should know the 6 strong acids, and they are hydrochloric, hydrobromic, hydroiodic, so they're all cousins of each other, if you will, right? It's a halogen group showing up there. There's a couple of really common ones: nitric acid, like we see in this problem, sulfuric acid, and then the last one that's usually referred to as a strong acid is perchloric acid. And again, you should know these 6 here. Just a little heads up, depending on the textbook author, depending on the chemist that you're talking to, there may be a few others. But we're going to stick with these 6 here. These are the most common ones that's referred to as strong acids. Now, besides these hydrolysis reactions, we have a few more sort of traditional type of chemical reactions that we see for these acids in particular. So let me just do one at a time here. So when you have an acid and a metal reacting together, what you form hydrogen gas and then some salt that's going to be in an aqueous solution. So let's do A first. Hydroiodic, it's just HI. Aqueous. Potassium metal, that's K, it's a solid. Hydrogen gas, we already know what that H2 gas. And then the salt, well, the salt here is coming from the iodine. So the proton, in a sense, gets transferred. It reacts from the hydrogen gas. What's left over is the iodide anion, and it is going to pair up with whatever metal cation is produced from potassium. And what we've learned in this semester is a potassium. It's in that first family of the periodic table, therefore it always takes on a +1 charge. Since the charges here are equal and opposite now, its salt formula is just simply Ki. Now, if we do a quick inspection of this equation, we have 2 hydrogens here and only 1 hydrogen there. Therefore, we need to balance this equation. I'm not going to fully break it down here. I'm just going to sort of take it a step at a time, because really, right now, it's just the hydrogen that is not balanced. So let's just walk our way through this. I need 2 in front here. That also affects how many iodines. Okay, so how can I increase the number of iodines? I need a 2 in front there. Well, it also affects potassium now, and then I go back and put a 2 in front of potassium, and it's balanced. You know, fairly typical for your balancing acts for these chemical equations. 2 to 3 steps, everything should probably come together. In the second one here, this one's not necessarily obvious what's going on, but it's going to be a neutralization reaction. For a neutralization reaction, what happens? Water is produced, and then guess what? A salt. Let me write these out. So hydrobromic acid, that's one we saw a second ago. Right? It's a cousin of the hydroiodic acid. Sodium oxide, it has this formula. I said water is produced, and then a salt. Let me save the salt for just a minute. Let me focus on the water part of things here. So how's that water produced? Well, the water is produced from the proton, and then this oxide here is actually a strong base. These oxide anions are really good at pulling protons off of molecules, especially when it is a strong acid. These two are not going to come together in a 1-to-1 ratio. Look at the charges. Okay, I need 2 of these to balance out the -2 charge there. And what I get is water. So that's where the water's coming from, is from this reaction. What's left over? Well, the things that are left over are these 2. Bromide, sodium. They come together in a 1-to-1 ratio, just like potassium iodide. And now that I have my molecular formulas in place, I can then go in and balance the equation. And I think I'll do the same thing I did before. I'll just take it one at a time. I'm noticing the sodium here. I got 2 sodiums. I mean, I need 2 in front there. Notice that I can't do this. That is an incorrect statement. Remember, plus charge, minus charge, equal and opposite. They're going to come together in a 1-to-1 ratio. This isn't going to change. I can't do this. If I want to create 2 sodiums on this side, I have to place it in front of the formula. So it also affects the bromide count. Okay, let's take care of it. Only 1 bromide is showing up here, so I need 2 more there. And then notice, 2 protons here, actually agrees with what I did earlier, and then 2 protons there. And then 1 oxygen, 1 oxygen. It's balanced. The reason I'm calling this a neutralization reaction, well, I'm producing water. I'm producing a salt. That's the definition of a neutralization reaction. And again, oxide is one of those strong bases. It may not have been mentioned too much in the textbook. Hydroxide is usually the one that's always referenced. That's one reason why I wanted to do this problem, just to show you there are other options in terms of bases than the ones that we dealt with. That's enough for the first video. The next one would be dealing with some of the calculations for acid-base chemistry. Okay, thanks.